My dear students, now we are going to look at a 3-bit synchronous down counter. The first step that we need to look at is determine the number of flip-flops required. As it is a 3-bit, it is also known as mod 8 synchronous okay, down counter. Other name for the 3-bit down counter is nothing but mod 8 synchronous down counter. So it will count from 0 to 7, then followed by 0 to 7. Okay, so 0 to 7, 0 to 7 is known as modulo 8 counter. Okay, so as it is 3-bit, we require 3 flip-flops because it is a 3-bit we require 3 flip-flops. What is the general formula is 2 power n should be greater than or equal to n, where capital N is mod n value. To design mod n synchronous counter, we need to satisfy this condition, where n is number of flip-flops. Okay, so in our case is 8. So 2 power n should be greater than or equal to 8. So what is the value of n? Okay, so greater than or equal to, if I make 2 power n equal to 8, n equal to 3. So for n is equals to 3, the minimum value for which this condition is satisfied is 3. So number of flip-flops required as 3. Or other way of interpretation is to represent 7 digits, 0 to 7 digits, 0 to 7 digits, totally 8 combinations. These 8 combinations can be represented with 3 zeros to 3 ones. The meaning is each position is for one flip-flop. So with 3 bits I can distinguish 0 to 7. With 4 bits I can distinguish, with 3 bits totally 8 different states, with 4 bits 16 different states. Okay, so likewise we need to look into, based on your counter design requirement, we need to look for number of flip-flops calculations. This is step number 1. Done. Next, step number 2, choose the type of the flip-flop. It is maybe mentioned in the problem, or you need to choose. Let's take the flip-flop in our case. Next, choose the flip-flop is done. That is step 2. Step 2 is completed. Next, what I need to do is draw the state diagram. So what is the state diagram is how exactly your counter has to behave. The state diagram is something like this. We have seen already for up counter. Similarly, we are looking for a down counter. Okay. So if you look at this, it will be at 1111, 110, 101, then 100, 011, 010, then 001, 000. So it will be moving from one state to other state. It is going down. Every time it is going one less than the previous state. This is known as state diagram. This state diagram is giving us an information how the states are changing in the flip-flops. How many flip-flops? 3 flip-flops. So we have 3 flip-flops. Flip-flop A, B, C. Let's say this is A. Let's say this is B. Let's say it is C. So what we need to do is, from these flip-flops there are inputs and there are outputs. Input, output. Input and output. This I call it as TC. This I call it as TB. This is I call it as TA. What is available is QA, QB, QC. What we try to do is, we try to get the expression for TA, TB and TC, which is functions of QA, QB and QC. It is also function of QA, QB and QC. TA is also function of QA, QB and QC. Once you get that, what we try to do is, we draw the circuit diagram. For that, what we do in the next step is, this is Step 3. Step 3 is done. So in step 4, what we try to do is we go for what is known as excitation table for flip-flop. Sorry, is it flip-flop? No, it's a counter. Flip-flop we know. Excitation. What is excitation table? Which will give output to input relation. Input to output relation is called truth table. Output to input relation is called excitation table. So we are looking for excitation table for counter because we are designing a counter. So we are looking for the output which is present state. Then we are going to look for next state. Then we are going to look at flip-flop inputs. So present state is, if it is 0, 0, 0. What is the next state as per your state diagram? For 0, 0, 0, next state is 1, 1, 1. Okay. For 0, 0, 1, next state is, okay, 0, 0, 0. So present state is 0, 0, 0, next state is 1, 1, 1. If present state is 0, 0, 1, next state is 0, 0, 0. If present state is 0, 1, 0, your next state is 0, 0, 1. If present state is 0, 1, 1, your next state is what exactly? 0, 1, 0. If your present state is 1, 0, 0, your next state is 0, 1, 1. 1 less than that, right? For 0, 0, 0 is 1, 1, 1. So for example, for 1, 0, 1, with the present state, next state is 1, 0, 0. Let's say this is QA plus 1, QB plus 1, QC plus 1. Whereas this is QA, QB, then QC. QA, QB, QC. Okay. So what we try to do is we look for TA, TB and TC. So for 101, for 101 is done. For 101 is 5. 110, 110 is 6. So next state is 101. If it is 111, it is 110. Right? So all states covered, all are covered, one less than that. Okay. So for 111, 110. For 000, 111. Next is 000, next 111. So it repeats. Totally 8 states have come. Done. So what I need to do now? Now I need to look for the flip-flop TA excitation table for T flip-flop Qn plus 1 and T input. For 0, 0 input is 0. For 0, 1 or 1, 0 excitation is 1. The meaning of this is present state is 1, next state is 0. Possible if input is 1. Present state is 0, next state is also 0. Input should be 0. So from outputs we are trying to look at the inputs. This is output. Output versus input is excitation table. For 1, 1 input is 0. So no change is, if there is no change to present state to next state, then input should be 0. If present state is different from the next state, input should be 1. As we have seen in these two cases, input should be 1. When input is 1, present state is different from next state. So we'll look for that and we try to compare QA with QA plus 1 and we'll look at the TA. What exactly the TA, so that we are going to get this sequence. So your present state is 0 and the next state is 1. So input should be 1. 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. Never it is same. So all 8 cases, it is being 1. So what we try to do is we will represent that. It is 1 for 8 different cases. Next for TB. So to get TB, I have to compare QB with the QB plus 1. Okay. So when we compare QB with QB plus 1, 0, 0 compared with 1. So different. So 1. And what about this? This is 0. So 0. And next 1, 0. So 1. Next 1, 1, 0. Next 0, 1, 1. Next 0, 0, 0. Next 1, 0. 1, 0 is 1, 1, 1. 0. Next you see here, for this 0 it is 1, so it is 1, right? For this 0, 0, 0, 0, 0, 0, so 3 zeros, same. Next this is 1, this is different, so input is 1. Next 3 ones and 3 ones, 3 ones here, 3 ones here. So 0, 0, 0. Done. Now we will look for expression for TA, TB, TC. So what we try to do is TA, TB, TC are outputs. What exactly the meaning of that is, we are processing QA, QB, QC, QA, QB, QC, and we are trying to get TA, TB, TB and TC. So TA is function of QA, QB, QC. So what we try to do is, this is what exactly combination circuit that we are going to add to the sequential circuit, combinational circuit that we are adding to sequence circuit to get a counter operation. So what we try to do is, we try to look at here and we try to put it in the K-map. So can I put a K-map here? Yes, sure. So I will take a 3 variable K-map, very simple. Here the inputs, what are the inputs we have? We have a QC which is MSB, QB and QA, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. So all ones, 1, 1, 1, 1, 1, 1, 1. This K-map is for TA. This is for TA. I will get expression for TA. So expression TA is equal to 1. Next look at the TB. So for TB once again the same process. What exactly? 1, 0, 1, 0, then 1, 0, 1, 0. Next 1, 0, 1, 0. Next 1, 0, 1, 0. So this is QB, QA, QC, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. So what I can do is I can combine these two with this two. So what is that? That is I am going to get is, this is expression, this map is for TB, I will get expression for TB. So TB turns out to be, okay, QA bar. Next I will take the another K map. The K map that I am trying to look at here, what I try to do is, I will take up the K map, okay. So what is going to happen is, we are going to draw the K map. From the K map, we are going to get expression for what? Expression for your TC. This is your QB, QA. This is your QC. Of course, it is 1 for 3. Is it 1 for Q? TC is 1 for 0 and 1 for 4. 1, 0, 0. It is 4. So it is 1. So I have to combine this two. Rest all zeros, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. This is a table for what? This is a table for TC. I'll get expression for TC as QA bar and QB bar. Okay. So on the whole, the expressions what I got here is, if I look at, the expression for TA is 1, expression for TB is QA bar, expression for TC is QA bar and QB bar. So with this, what exactly that I am trying to do is, we can draw the circuit diagram. The circuit diagram will look like this. So what I do is, I'll take 3 flip flop 1, flip flop 2, then flip flop 3. From these 3 flip flops, what I try to do is, I am going to take the output, of course. This is my output. This is the input. There is a common clock. Synchronous circuit means common clock. Common clock is given here. This is a clock signal. So this is flip flop A. All are T flip flops. This is flip flop C. This is QC. This is QB. This is QA. Available is QA. This is QB. This is QC. If you want QC bar, of course it is available as QC bar. If you want QB bar, of course here is QB bar available. If you want QC bar is also available. So what we try to do is, this is what exactly known as TC, this is TB, this is TA. This TA should be connected to always 1 from this expression. From the other expression, if you look at TB, TB should be connected to QC bar. So QC bar is available. This we are connecting it to QC bar. Is it QC bar? No, it's a QA bar. This is QA bar. Sorry, it's A bar. So connected to QA bar. Next QA bar, QB bar, and we have to AND it. So what I try to do is, just I will erase this TC part. I will take an AND gate. I will take an AND gate, and to that AND gate, what I will try to do is, one of the input I will give it to is QB bar and QA bar. From where I will get? One I will get from here, another one I will get from here. I am not drawing the line, instead I am presenting here. If I draw the line, it will make looks like complex. That's why I am doing. Even you can do that also. If you want, you can do that like this. You can put like this, then connect like this. Okay. What I can do is, I can take this like this. I can go like this. I can connect it like this. Okay. So either way it is possible, or I can simply show it without any complexity, or I can show directly from the connections. Okay. So this is how one can. This is last step, step 6, where we have drawn the circuit diagram. This is complete of the design. So how exactly it will start with? It will start with 1 1 1 to 0 0 0. Every time whatever you load, anywhere you load, any value you load. Let's suppose you load 1 1 0 and you start working. It will become 1 0 1. Then this is 5. Next 4 3 so on and so forth. Okay. So this is how one can work with a 3-bit synchronous down counter.